In this fifth module, we are in the process of discussing the internal structure of hadrons and strong interactions. In this third video, we discuss mesons, which are bound states between quarks and antiquarks. After following this video, you will know the basic mechanisms that bind quarks and antiquarks to form mesons, and their excited states and their spectra, which provide information about the nature and the behavior of the binding force. In addition to the baryons and their resonances, which we have already treated in the previous video, there are bound states between quarks and antiquarks, which we call mesons. If their quantum numbers are right, they can be produced in vacuo by a virtual photon as shown in this Feynman diagram. For light quarks, their mass is dominated by binding energy. For heavy quarks, their mass is slightly lower than the sum of the masses of the corresponding quark pair. An example is the production of rho mesons, a bound state between light quarks, which is shown in this Feynman diagram. Resonances can also appear as intermediate states in hadronic reactions. In this case, there is obviously more freedom regarding their quantum numbers. In general, bound states between quarks and antiquarks have a rather short lifetime, especially if heavy quarks are involved. This is due to the substantial phase space available for their decay. The energy dependence of the electron-positron cross-section around a resonance generally follows a Breit-Wigner function, which is shown in this equation. M is the mass and gamma is the width of the resonance. The cross-section is reduced to half of its maximum value, sigma max, for square root of s equal to m plus or minus gamma over 2. The lifetime of the resonance is the inverse value of the width. Tau is equal to 1 over gamma. The form of the Breit-Wigner function resembles the squared amplitude of a classical damped oscillator. Square root of s corresponds to the frequency of the external periodic force, m to the resonance frequency, and gamma to the damping factor. The cross-section in this analogy appears as the squared amplitude of the oscillation as shown in the graph on the left. For resonances between light quarks, such as rho and omega, one observes width from a few MeV to 150 MeV, corresponding to lifetimes between 10 to the minus 22 and 10 to the minus 24 seconds. They are produced in a resonant manner by the intermediate photon when the mass of the virtual photon is sufficiently close to that of the meson. When produced this way, they must obviously have spin 1 and charge 0, just as the photon does. They decay into pions. Around a mass of about 1 GeV, one can produce the phi resonance, which is an SS bar bound state, which decays into strange particles. Its width is narrow, of the order of 4.4 MeV. Around 3 GeV, we find the J-psi resonance, a CC bar, the lowest lying CC bar bound state, as well as its excited states, the psi mesons. Their widths are small, about 90 keV for the J-psi itself. The lifetime is thus long, and the E plus E minus hadron cross-section is significantly enhanced around the resonance energy, as shown in this plot. Close to 10 GeV, the epsilon resonances are produced, made of BB bar pairs. We see on the right the E plus E minus 2 hadrons cross-section around the epsilon 1s resonance and its excited states epsilon 2s and epsilon 3s, all mesons formed by BB bar states. The states are distinguished by the relative angular momentum of the two quarks. The spins are always parallel to produce a vector meson. The study of resonant states, especially those of heavy quarks, allows to better understand the potential generated by the strong force that binds quarks and antiquarks into mesons, as well as also the decay mechanisms for heavy quarks. As an example, the figure shows the mass spectrum and decay scheme of CC bar and BB bar resonances. The energy levels indicate that the potential between two quarks has two terms. The parameter alpha s is of order of 0.2, is the strong interaction analog of the electromagnetic fine structure constant. The first term diminishes with distance. The second term, on the contrary, grows with distance and keeps the two quarks from being separated. The constant in this confining term is of the order of 1 GeV per Fermi. In video 5.4, we will discuss in more detail the properties of the strong interactions which provide this binding force. The peaks of the cross-section around resonances invites to build storage rings for the mass production of the corresponding states. The collider Daphne in Frascati, Italy, is one such factory dedicated to the production of phi resonances. The Beijing E+E- storage ring BEPC produces J-psi and psi mesons. The PEP2 collider in the United States and KEC-B in Japan are factories for the upsilon and other BB bar mesons. The systematic decrease of the width of with the mass of the resonance could make you believe that a TT bar resonance would be very narrow and thus have a long lifetime and a significant cross-section. This, however, is not at all the case. The top quark is so heavy, of the order of 175 GeV, that the phase space for its decay becomes enormous. The T-quark lifetime is thus extremely short. It decays before it can even form a bound state. Consequently, there will be hardly an increase in the E+E- cross-section at the threshold for the production of pairs of top quarks. In the next video, Mercedes will discuss what all of this means for the properties of strong interaction.